Okay, everybody, thanks for joining us this week. This week we have RJ Graham talking to us about substantial extension of the lifetime of the terrestrial biosphere. This was a talk, this was a paper that was recently posted to arXiv and I think is in PSJ now and came
Will
up in
be.
some recent discussions in a week. Okay, excellent. So take it away, RJ. We're looking forward to hearing about it.
Thank you. And not in a week, but it will be. But I do, yeah, it's still proofing and stuff, so there'll be a little bit before it actually comes out. And in fact, I'll probably uh add some citations and stuff. Um, yeah, thank you for the introduction. Yeah, my name's RJ Graham. I work at the University of Chicago as a postdoc, as part of the NASA postdoc program thing. And yeah, the first project that I started when I started that with Dorian and with Itai Halevi is this project, substantial extension of the lifetime of the terrestrial biosphere. And sort of inspired by some of my PhD work looking into different formulations of weathering that might do a better job of representing the climate and yeah, the climate dependence of silicate weathering. And I'll go into, some of that. So yeah. So this collaborator, Itai Levy, he is a professor at the Weizmann Institute, and this collaborator, Dorian Abbott, he is a professor at UChicago, and they were the co-authors on this. So start, land plants. So yeah, I'm talking about the lifetime of the complex terrestrial biosphere, quote unquote. But when I say that, I'm just talking about land plants for the purposes of this paper. And the reason for that is land plants are a big part of the terrestrial biosphere, the complex terrestrial biosphere. They're 80% of the biomass. They are, half the primary productivity, the other half being plankton in the ocean. And so, they're sort of the engine. They're the engine of all of the big creatures that exist on Earth. They're capturing this energy and making it available for big lumbering behemoths like us to use. So they're really important for they're the kind of they're the linchpin of the complex terrestrial biosphere, you could say. And so this plot just shows the right side is just to zoom in on animals. The left side shows like the Earth biomass, and you can see plants just kind of dominate it. And so when I say the lifespan of the complex terrestrial biosphere, I mean ultimately the lifespan of land plants on Earth's surface when I discuss that. And so there are two kind of primary pathways people have suggested that land plants might eventually go extinct. And the first one, and the one that people talk about the most, is CO2 starvation. So plants need a certain amount of CO2 in the atmosphere to do photosynthesis. They're drawing their carbon out of the air. And so if the CO2 was too low, then the chemical reactions that are necessary would be too slow, and plants ultimately couldn't produce net biomass. And so for the rest of this talk, I'll call that CO2 starvation. And then the other possibility is overheating. Once you get hot enough, lots of processes don't work right anymore. And so either you could drive your land plants extinct by pulling all the CO2 out of the atmosphere or by making the surface too hot. And so in the future, the sun is going to keep brightening. It's been brightening its whole history, and that's going to continue. Right now, we're here at the one, and as in a billion years, it'll be 10 or 15% brighter. So it's that's significant, and that's going to make the surface of the Earth warmer. And there will be a response to that from the carbonate-silicate cycle, which is sort of the presumed to be kind of one of the main mechanisms that's kept Earth habitable throughout its history because uh, there's always CO2 entering the atmosphere from volcanic outgassing and various processes that produce CO2 in the interior of the atmosphere or in the interior of the planet. And if you didn't have a sink for that CO2, it would just keep building up and eventually look like Venus. You just have a lot of CO2 in your atmosphere, be very hot. But on Earth, there's a water dependent reaction, silicate weathering, that um, pulls CO2 out of the atmosphere, the dissolution of silicates on the seafloor and continents. And in this case, we focus exclusively on the continental component, but the dissolution of silicates produces cations that ultimately react with carbon in the ocean to produce carbonates, and that pulls CO2 out of the atmosphere. And that process is climate dependent. It goes faster when it's hot, slower when it's cold, faster when there's high CO2, slower when there's low CO2, which makes a negative feedback on climate. And so as the sun brightens, as the sun has brightened over time throughout Earth history, uh, the CO2 in the atmosphere is drawn down in response because when you brighten the sun, you make the surface hotter, you make the silicate weathering rate go faster, and that will pull CO2 down until the silicate weathering rate has slowed back down to operating at the same speed that outgassing is putting CO2 in the atmosphere. So it keeps balance between the influx and the outflux of carbon. And that process has responded to the brightening of the sun throughout Earth history, drawn down CO2 from very high levels in the deep past to significantly lower levels now. And in the future, as the sun keeps brightening, that's going to continue. And so you have a situation where if CO2 gets low enough in the far future, as the sun gets bright enough, then that could eventually drive land plants extinct. And alternatively, if for some reason the CO2 didn't get low enough to starve them, but the sun is still brightening. So if the carbonate silicate cycle for some reason operated in a way that prevented the CO2 from getting too low, then nonetheless you would still eventually get hot enough that plants would go extinct. And even if you had really crazy evolutionarily robust plants, eventually they're going to be killed by the runaway greenhouse. And so there's these two kind of broad categories of eventual plant death mechanisms that we'll explore here. So what's going on? Like why does photosynthesis have the reaction it has to the climate? And ultimately it's because, or at least the deepest fundamental reason is it's being catalyzed by a protein called rubisco, which is the probably by weight the most common protein on Earth. And Rubisco, yeah, it's Rubisco's response here that is leading to this temperature and CO2 dependence of plant productivity. Essentially, yeah, you can see here this plot shows the rate of photosynthesis as a function on the x-axis of surface temperature, and then for the different curves, they're with different background CO2s. And so you can see like as you crank up the surface temperature, you eventually reach a peak in photosynthetic efficiency, and it starts dropping off. And also, as you have higher CO2, your peak moves both to higher levels and to higher temperatures. And so that's sort of the qualitative pattern of how productivity responds to climate and how we're going to represent it. Now, an important point to make that is going to be important for the results of the paper is that there are kind of two important major pathways of photosynthesis, two major metabolisms that are used on Earth right now, C3 and C4 photosynthesis. C3 is most of it, like 80% on modern Earth. It's like trees and stuff. C4 is a more recent evolutionary innovation, which allows for plants to operate at lower CO2s and with less of a temperature dependence because there is an internal CO2 concentration mechanism. Basically, they have these little sheaths inside their cells that allow them to pump CO2 up to higher levels. And so they're less sensitive to the background CO2. And so the C4 plants have appeared in the past 30 million years or so, but they have really changed the like kind of the climate dependence of plant photosynthesis. And that's important, and we'll talk about that. But so the idea here, okay, we have land plants. They're the cornerstone of the complex terrestrial biosphere. They're the reason we can exist. How far into the future might they be able to exist? And are they going to die due to CO2 starvation or due to overheating? And that's sort of the objective of this paper. So there have been quite a few, previous attempts to calculate this. Sort of the classic one that people cite a lot is Caldera and Casting 1992, which I'll refer to several times throughout this talk. And if you see CK92 written, that's what I'm talking about. And this plot kind of shows their results. So as the insulation increases, that's this S over S naught on the right hand y axis. As that increases, your carbonate silicate cycle responds by drawing down CO2, as noted before. And what's going on here with this two-pronged CO2 plot is that they have an atmospheric CO2, and they also have a soil CO2, because another important component of these models is that plants themselves are thought to accelerate silicate weathering by uh, basically elevating the amount of CO2 in the soil by, for example, there's root respiration happening, there's organic matter decay happening in the soils that, if there's higher productivity, there's more organic matter and that happens faster, things like that. And so as productivity goes up, soil CO2 goes up, and also the other way around. As productivity goes down, soil CO2 goes down. So you can see here as we go into the future, x-axis is time in the future, and as the sun brightens, your CO2 is dropping, and in fact, your soil CO2 and your atmospheric CO2 are approaching the same value. And the reason that's happening is because here on this, you can see on this the lower figure, which is plotting biological productivity versus time, and then also surface temperature. You can see biological productivity is dropping rapidly and eventually hits zero. And at the point where it hits zero, that's the point where soil CO2 and atmospheric CO2 are equal again. And so yeah, what these guys found was that in about 0.9 gigayears, or about 900 million years, plants will die off due to CO2 starvation. And they find like there's a kind of monotonic drop off in your atmospheric CO2 as your sun brightens in the future. And that's sort of the standard picture, is that in the far future, as the sun brightens, CO2 drops, and in about a billion years, plants go extinct, everything dies. That's the thing that typically is discussed. And that's not the only paper that's looked at this. There have been a bunch that have kind of done versions of this calculation. And if you look on the left side, that's where all of these, that's the number for the lifespan, where if it was one, it would be 1 billion years. And so you can see they really cluster around a billion years, basically, other than in that very first Lovelock and Whitfield paper, but they didn't actually even do a calculation. They're just doing kind of a qualitative thing. And yeah, so quite consistent result that the favored kill mechanism is CO2 starvation, although there are a few cases where you can get temperature kill mechanism, but quite consistent result that it's mostly CO2 starvation and mostly you last about a billion years into the future. And they also use, I'll explain what TE and beta are in a slide or two, next slide actually, but those are related to the parameterization of silicate weathering. The TE is about I'll go into it, but basically you can see that these papers mostly use quite similar values for their silicate weathering parameterizations too. And that results in quite similar estimates for the future lifespan of the biosphere. And this is starting in 1981, and then the most recent one is in like 2023. So yeah, previous estimates made some assumptions that in this paper that I'm presenting to you, we questioned. So firstly, okay, so yeah, here's the equation for silicate weathering, the climate dependence of silicate weathering, and basically what it shows here, W over W ref is just the overall weathering rate, and then a reference weathering rate. V over V ref is the CO2 outgassing rate, and so they're set to be equal because again uh, the negative feedback of silicate weathering tends to bring the weathering rate into parity with the outgassing rate. But so there's a temperature dependence and a CO2 dependence. P soil is the partial pressure of CO2 in the soil, which is dependent on the productivity model as well as the atmospheric CO2. But so here we're talking about the temperature dependence of silicate weathering in these models, which we can represent with just a simple E-folding temperature. So basically what TE is if you were to increase the surface temperature of Earth by a factor of TE, then you would increase the weathering rate by a factor of E. So that's what makes it an E-folding temperature. And so typically in the previous calculations, people have assumed a pretty strong temperature dependence, which means a small e-folding temperature, which means you only have to change the temperature a small amount in order to change the weathering a lot. And typically you get a value like this around, between 10 and 15, basically. But there have been like kind of a series of papers in the past maybe 5 years, or let's see, I guess in the past 7 years, based on the 2017 one, where people have tried to estimate this TE value for like Earth as a whole, rather than in the way that people typically did it in the past was, you take a rock, you put it in some water, you increase the temperature, and you look at how much faster it dissolves in the water under the higher temperature. Okay, that's reasonable, but the carbon cycle on Earth is very complicated. It may well be that there's all kinds of other processes going on that affect things in a way that's independent from the like chemical kinetics that you could really constrain with those sorts of lab experiments. And so people have approached it in different ways. This Brantley paper attempts to kind of like synthesize a bunch of different stuff like field lab modeling to give a best estimate of an e-folding temperature of 31 Kelvin, which is significantly larger, significantly weaker temperature dependence. But on the other hand, there's another paper, Deng et al. 2022, where they look at the sort of the latitudinal dependence of how much clay has been altered on Earth over time, and they come up with a quite strong one. But the preponderance of recent estimates of the kind of the e-folding temperature have suggested it's a lot weaker, i.e., a lot larger than almost all of the calculations that have been done to do this estimate in the past. So you get 31 Kelvin, you get 41 Kelvin, you get 34 Kelvin, you get 31 Kelvin, and those like Christensen-Totten ones are based on doing an inverse carbon cycle model where you constrain a lot of the carbon cycle parameters by using geochemical proxy data and doing like a Bayesian MCMC thing where they pull a bunch of values, figure out which sets of parameters for the weathering model reproduce the previous trajectory of CO2 and surface temperature based on proxies. And so basically, it seems like the carbon cycle responds more weakly to temperature than people have thought in the past. Okay, and yeah, right. I talk about this carbon cycle model. They're using this data. They're using these dots to constrain the output of their model, which is coming from these lines with uncertainty estimates based on the envelopes. And as I said, they do this inversion, and you end up with a much weaker TE than CK92, for example, used that 13.7, and that's all the way over here. CK92 is sort of on this like on the less likely end of things. You're over a standard deviation out from the median, and the median that they get is more like 31 Kelvin. Okay, and so similarly, so there's that direct temperature dependence, but there's also a direct CO2 dependence, which is this beta, this power law. And you the same thing applies basically. People have used certain values, and it seems there's a wider range of possibilities than people have acknowledged. And that again, from this, and in this case, the CK92 value they chose is well within the range of plausible values, but it's just you got a huge range that is kind of permitted by uh, proxy evidence. And so the fact that people, for all of these previous attempts to calculate the future lifespan, they just kind of pick, a really strong temperature dependence and sort of a random weak CO2 dependence, arguably would lead to biased results systematically. And so the one more big assumption that I think most of these papers get wrong is they seem to like kind of assume that plants are weaker than they are. Um, so for example, the CK92, the Calder and Casting 1992 paper, they assume that plants will die out when CO2 reaches 10 parts per million and or when surface temperature exceeds 323 Kelvin. But uh, I mean, those are just certainly too conservative. So there are C4 plants that can go down to 3 parts per million, even lower. In fact, I use 2.9 parts per million as the lower level in this paper because that's what comes out of the photosynthesis model, which is a model that's actually based on like the stuff people use to model photosynthesis. So yeah, so the CO2 starvation threshold, people have been too conservative about that. Assume they die at 10 parts per million, even though there's good lab evidence that you can have C4 plants photosynthesize at much lower levels than that. C3 plants, on the other hand, the ones that don't have the concentration mechanism, they'll die by about 150 to 100 parts per million. So that's valid, but the C4 plants are really a lot stronger. And service temperature also. So the kind of standard assumed temperature limit is 50 Celsius or 323 Kelvin, but that's certainly too conservative. For example, there's a grass in Death Valley that grows exponentially every summer when Death Valley is getting to about 50 Celsius. It's that's like its favorite situation. So clearly that's not like a biological limit to plant function. If there's a plant that loves it so much that it like waits for it to start like expanding and spreading like crazy. And similarly, in Yellowstone National Park, there are, you've got geothermal heat, you've got really hot springs, that's what they're called. And when you get close enough to those, they're quite devoid of plant life. But there are certain quite bizarre plants that, in symbiosis with a certain fungus, when that certain fungus is infected with a certain virus, uh, they can survive repeated very long-term exposure up to 338 Kelvin, so 65 Celsius. So much, much, much hotter than the suggested upper limit. And so we take 2.9 parts per million and 338 Kelvin as the CO2 starvation level and overheating level, just based on the literature on plant uh, resilience. And that fungus thing is crazy. You can put that fungus into other plants, and then they gain this heat tolerance. It's kind of wild. So developed a model to try and take into account the things that I just said. So oh wait, also there was a question, and then it just disappeared. Um, uh,
Yeah,
and I yeah,
can you question there, or do you want to wait till the end?
happy to take it.
Oh, can you go back to the last slide?
Yes.
So key to this CO2 starvation is, of course, the photo respiration is what the O2 content is. It's because
Yeah.
Rubisco is also oxygenase. So have this had did not quite up to speed. Are the previous studies, are they varying the O2 content of the atmosphere along with the CO2?
I believe there's just one that's attempted that, the Ozaki and Reinhard, which is this one, the from
Okay.
2021, and they have, yeah, they use like, I believe they use COPS or COPSE. I don't know how you pronounce it, COPSE. It's a model that it's like a biogeochemical model that has a bunch of components, including the oxygen stuff. And that, in fact, that's the point of their paper. They're actually looking to see when, to see how the future oxygen evolves on Earth and estimate when, for example, the atmosphere deoxygenates. Um, I don't account for that, and no one else does. I do think I may extend this model using something at least inspired by the Ozaki one, because I do think the oxygen stuff is a very interesting question. And you're right, it's about the ratio for the Rubisco function. And so the oxygen partial pressure is just
Right.
as relevant as
No,
CO2
it
partial
is.
pressure.
It is totally part of the equation. I mean, you can't leave the
Mhm.
oxygen out. So I was talking actually with Bob Blankenship about this, and Rubisco does not have a lower CO2 limit for carboxylating a CO2. So it's mainly the balance between the O2 and CO2. But the thing is, plants are aerobic. So I think we also have to look at what's the lower oxygen limit for aerobic plants. So anyway, that's for future work, maybe. Okay.
Totally. No, I agree though.
Okay.
And that is a big caveat to this is not dealing with oxygen explicitly, just assuming it's constant in the background.
Okay,
And
cool.
sorry, I didn't mean to interrupt you though. Did you have something else to say?
Chris has a question. I don't want to take you.
Oh,
I don't want to
Mhm.
divert you. Thanks.
Just real
oh, go
quick,
ahead.
the functional form for weathering, it was temperature, but not there was nothing about precipitation in here, and I'm just wondering
Mhm.
if you just arbitrarily increase temperature in the future. I mean, precipitation can scale with temperature a lot of the time, but not necessarily like global mean precipitation. Not in all situations. For example, if you just keep adding CO2 to the atmosphere, it doesn't monotonically go up with temperature. in hot climates. But is that important, or is that just not relevant if the forcing mechanism is the sun?
I think that it may well be relevant. In fact, the reason that I did this partially was because yeah, when you represent silicate weathering with a somewhat different model that is more hydrologically dependent, you end up, I mean, that's essentially equivalent. Like, so, okay, so with typically when people do these silicate weathering models, they're thinking about the temperature dependence as being, yeah, related to the chemical dissolution temperature dependence of silicate minerals. But then, as Chris brought up, another uh, temperature coupling between weathering and the climate is the fact that as it's hotter, hydrology goes faster. You get more rainfall, and that pumps more water through the weathering zones and can ultimately lead to faster weathering in certain regimes. And part of the reason that I did this paper is because you can, if you zoom out to the global mean level and you're just, you can, if you want to represent weathering as being dependent on hydrology, one way to do that is to represent it as having a very large TE, basically, because like the precipitation is essentially linear in surface temperature up until you get to really high levels, at which point you do get different behavior, non-monotonic. But the linear behavior of precipitation with respect to surface temperature leads to basically like if you had weathering that was just one-to-one dependent on hydrology, you would have a kind of a linear temperature dependence of weathering, and that's similar to having a really large TE, like because the exponential, you zoom in on it enough and it looks like a line basically, and so the the high TE weak temperature dependence like parameter regime of this is similar to the regime where weathering is dominated by hydrology. But I agree that when you get to really high temperatures, then the hydrologic cycle changes its structure somewhat because of various energetic uh, limits that may matter a lot because it may change the kind of the structure of the carbon cycle at hot enough temperatures. And that is a thing that we want to touch on in the future because, yeah, there's some weird stuff with the hydrological cycle at very high temperatures. But in here, we don't explicitly account for hydrology. It's folded into the temperature dependence of the weathering. If yeah, right. Okay. Yes. Yes. Okay. Yes. Basic point here. Previous attempts have assumed plants are easy to kill. Okay. Developed a model doing all this stuff. The sun, you've got the Earth's climate, you've got silicate weathering, and you've got plant productivity. And the sun, its only effect is to change the climate set point. Increase the sun, then you make it so that you reach a given temperature at a lower CO2, basically. And we have the just the standard model for the solar brightening over time. The climate can affect plant productivity. It can either make it go faster or slower. That's why I made it purple. So, if it gets hotter, plant productivity may fall or it may increase depending on where you are to start. Plant productivity itself, higher plant productivity leads to higher silicate weathering. And so the productivity directly affects silicate weathering, and then climate also affects silicate weathering. Because higher CO2, faster weathering, higher temperature, faster weathering. Silicate weathering itself then feeds back onto the climate because it's the CO2 sink. And so this is just sort of a simple schematic of the structure of the model. Uh, and the plant productivity is also, it has a C3 and a C4 component. But okay, so right? I already showed kind of what the silicate weathering equation looks like. Then I wanted to also just show like I said, the soil CO2 is not the same as the atmospheric CO2 because there is this productivity effect where plants are making it so that the soil has a larger difference compared to the atmosphere. And so with higher net productivity, you have higher soil CO2 compared to your atmospheric CO2. And that matters a lot, actually. That leads to some interesting dynamics with how the climate trajectories unfold. This is just a simple, this is just to show kind of what the productivity in C3 and C4 plants looks like as a function of CO2 and surface temperature. And so, yeah, I guess the most interesting thing, yeah, you can see quite clearly that above maybe 100 parts per million, the C4 productivity is quite independent of CO2. I think that is maybe the most key point here. So CO2 being the x-axis. So if you move rightward, you're increasing your CO2, and once it passes a certain point, that doesn't increase your productivity anymore, which is due to the C4 plant's abilities to concentrate CO2 in its bundle sheets, like I said. So and C4 plants crazy. They like I said, they popped into existence maybe 30 million years ago, but they've arisen independently from C4 plants like 30 or 40 times, like in that period. It's ridiculous. It seems to be a very easy evolutionary innovation to make, which is relevant for thinking, evolution maybe obviously is going to become relevant here. And so this completely ignores evolution. We can talk about that. So I make this simple photosynthesis productivity model based on some papers that have models of C3 and C4 productivity. And it's kind of hard to tell how to validate that. One way was to actually just test against estimates of productivity from the past. So there's this paper from a couple of years ago that tries to estimate productivity based on oxygen isotope stuff. And so for a given, climate configuration, it suggests that the productivity during the glacials was maybe between 0.55 and 0.87. Our model produces something on the lower end of that range, but within the range. So it isn't crazy, is the point. But then the final point, you've got a climate model. So it's closed by requiring that OLR equals outgoing long wave. This is just an OLR plot as a function of temperature and CO2. And that it's the same OLR that's used in caldera casting. So let's get the results finally. Geez, sorry. So we ultimately, when we make the changes that I suggested, so when we change the weathering parameters and we allow for plants to, be more resilient as they seem to be, we end up getting quite different results. So the pink lines in these, or salmon, or whatever you want to call them, they're using the median weathering parameters from that Christensen-Totten 2017 inversion that I showed you some of those plots from, where they tried to estimate the best guess of these parameters for reproducing paleoclimate observations. So the salmon one is using those parameters. The black one's using the CK92 parameter. So it's using the old school, the parameters that were used in the famous paper from 1992 by Caldera and Casting. And the top panel shows you the C3 and C4 productivity for both of those. So there's 4 lines, and it doesn't show the total productivity. So if you perhaps poor design on my part, but you need to add those together to get the total productivity. A dashed line and a non-dashed line in the same color. But interesting thing. So with the KT17 parameters, C4 productivity stays really high for like a billion years because C4 plants are so able to operate at low CO2s and without worrying about CO2 changing. The C3 productivity in both cases drops monotonically with time. So, in the KT17 paper, trees will stop existing in about 800 million years. Now we get to so the more like relevant differences though. So if we look at the CO2 concentration versus time, so you can see it's a monotonic drop off with the CK92 with the black, but with the KT17 you get this kind of rolling trajectory, which is kind of interesting. And it's because basically, so the plant productivity feeds into weathering, right? And so as the plants die off, you have less and less plant productivity. And that means that as the plants die off, they are pumping the soil CO2 to higher or to less and less high levels. And so basically, like what is happening with this rolling thing is as the plants die off, you're getting to a point where that is a large enough decrease in the weathering rate to result in the necessity for a higher atmospheric CO2 to actually balance the overall carbon cycle, right? Because the plants hold the soil CO2 at a higher level than the atmospheric CO2, and the soil CO2 is what's actually feeding into the weathering calculation, right? But as the plants die off, the soil CO2 is dropping relative to the atmospheric CO2, and if that's a large enough effect, that can that can lead to atmospheric CO2 actually increasing despite the brightening sun. That's not great for the, thermostatic kind of behavior of the silicate weathering feedback because it leads to hotter temperatures. But it's great for plants that don't want to die by CO2 starvation because you ultimately end up not ever reaching a very low CO2 and so plants live until they reach the super hot surface temperature that kills them off. And so you end up getting an extra maybe was it extra 500 million years in this case. And if we were using that 10 part per million threshold like they do in the original CK92 paper, then it would end up being about 8 or 900 million years, similar to the original model. So it reproduces their results. But yeah, important point is that when you switch to more realistic weathering parameters, you seem to get a significant lengthening of your lifespan. And this sort of goes through and shows that in a more broad way. So on the x-axis, you have the CO2 concentration. On the y-axis, you have the global mean surface temperature. The so you have all these green curves. They are trajectories of Earth's future with different assumptions about the weathering parameters. And the assumptions are represented by these numbers. These numbers are just the product of TE and beta, TE and beta being the temperature sensitivity and the CO2 sensitivity. Because it turns out if you're holding your model at modern outgassing, then you can math it out a little bit and show that really the thing that's affecting the results is not TE or beta in isolation, but their product. And so that's why I represent it this way. And so for ones with really strong temperature dependence or really weak CO2 dependence, you end up rapidly going to CO2 starvation. Right. Oh, yeah. And the orange curves are the climate model curves, basically. So like at different time periods as the sun brightens. And so starting right here is right now, 0 gigayears in the future, SF equals 1. At 460 million years in the future, SF is 4% higher, et cetera. And so time is increasing in the upper left direction. And yeah, so as you have different weathering parameterizations, you end up following very different trajectories. And there's a threshold point where you switch between overheating and CO2 starvation as your kill mechanism. And that is like where the longest lifespan is. Basically, if you're dying simultaneously by CO2 starvation and overheating, that's when you've extended your lifespan as much as possible. That ends up being about 1.86 gigayears. And as you can see, the CK92 is over here, well within the CO2 starvation side, because when the trajectory hits the black line, that means it dies by CO2 starvation. That black line is just where the minimum CO2 is, and the red line is just where the maximum temperature is. So when trajectories hit the red line, they overheat. When they hit the black line, they die by CO2 starvation. And yeah, the KT17 is over here, smack in the middle of the overheat, and the CK92 is smack in the middle of the CO2 starvation. And so there's a fairly wide range of parameters on either side of this KT17 where you end up still overheating rather than dying by CO2 starvation. And yeah, it's significantly longer than previous estimates. Okay. Similarly, yeah, this shows the same thing in a different kind of picture. So beta times TE, again, the product is what matters. And though in this case, we're just looking directly at the time until land plant extinction from right now. And so you can see that as you increase beta times TE, meaning as you make your model less temperature dependent or more CO2 dependent, you go from a short lifespan of rapid CO2 starvation to a long lifespan of CO2 starvation and overheating to a slightly less long lifespan of overheating. And you can see the ways in which changing the assumed thresholds changes these answers as well. Similarly, outgassing rate, I'm sorry, I'm going a little bit over now, but so the different colors here are just different outgassing rates. The pink one is one times modern. The darkest one is a quarter of the modern. So on the left side, you have those CK92, the CO2 starving ultimately simulations. And in the case of CO2 starvation, the outgassing matters a lot. You decrease the outgassing and you starve a lot earlier. In the case of overheating simulations, the outgassing doesn't matter so much, which makes sense. You basically, if you decrease your outgassing rate and your planet's going to die by overheating, you slightly delay when you die by overheating. Oh, right. And In the case of changing the outgassing rates, it does matter. Like the beta and TE have independent effects, and so you can't do that product thing I was talking about before. But you can see it's interesting. If you start off dying by overheating, then yeah, you decrease your outgassing rate a lot, and it can actually just like continually increase your future because you're just delaying your eventual dying off. In this case, again, y-axis is time until extinction, x-axis is CO2 outgassing rate. And so for any of these simulations, like the CK92, it started off in the CO2 starvation regime. So you decrease the outgassing rate, you're always decreasing your time. But if you start off in the overheating regime, decrease the outgassing rate, you can have a longer time. It's kind of interesting. And similarly, the same thing is decreasing your outgassing rate would be in this very simple global mean model would be like increasing your land fraction is the same effect in these models. And so both of those are things that are supposed to happen in the future. Continents growing, outgassing rate decreasing. And so if we're in the KT17 regime, then that's actually like good news for extending the lifespan, which is somewhat counterintuitive. Yeah. Okay. So yeah, that's it. Using best estimates of weathering parameters and using the literature on when plants die, under what conditions plants die, it seems like the future lifespan of Earth's biosphere is quite a bit longer than previous estimates have been making. And instead of dying by CO2 starvation, it seems like it probably will die via overheating. And an interesting thing is, and I didn't mention this in a slide, but using that 65 Celsius as your overheating, you're actually like right there. Like your maximum temperature for your plants is pretty much like right in the range of when the moist greenhouse kicks in on Earth. And so like even if you were to find, oh, it turns out that plants, they'll evolve and they can actually live up to 350 Kelvin. It wouldn't matter that much because once we're in the regime of surviving up to about to 338 Kelvin, you're probably going to have a very wet stratosphere pretty soon, and then you're going to start losing your ocean, and then you're going to really die off. And so point being, this seems to kind of like a lot to potentially carry the ability of the complex biosphere to exist kind of just like up to the boundary where like total overall habitability might disappear potentially, either via the moist greenhouse or potentially via the runaway greenhouse. No one's really sure which one happens when, etc. But yeah, but on the other hand, there's still a lot of uncertainty in the parameterizations, and it still could be that CO2 starvation would be, it's hard to say, but the people hadn't used wide enough ranges yet, and I think it was useful to do that. Yeah, okay, that's it.
Okay, great. Thank you, RJ. That was really great. So if people have questions, maybe they can raise their hand and I can pick them if there are some questions. I know that Jim had a question earlier, but then he backed out. So,
I'll raise my hand again.
yes, go for it.
Yeah, no, my earlier one was, I was going to remark on the hydrologic cycle, but then you answered the question basically. That's tied into the temperature dependence, becomes very important. And I'm just wondering, can you go back to that last graph that you showed? Well, maybe it was the one before that. When you get up to, I guess my comment was going to be that when you get up to about 340 K, where's the one that shows the temperatures increasing with time? Okay, so that one, yeah. By the time you get to 340 K up there, you are right at the runaway greenhouse threshold. So as you said, all bets are off there. There, the hydrologic cycle really does you in.
Oh yeah.
What did you use for temperature for maximum temperature for complex life? I forget.
338. And that was based on this, where's that? Yeah. Dichanthelium lanuginosum, which can survive up to that temperature. And it's pretty like seriously, like they would like do it for like 14 hours at that and then 10 hours off. Like they're doing like a diurnal cycle type thing and for weeks and it lived. It's ridiculous.
Okay, but of course, for mammals like humans, the upper temperature limits are much lower.
Totally. Yes. Yeah. In there as they exist now. I 100% agree. Uh, yeah. So yeah, the idea of yeah, calling this like the complex biosphere limit is yeah, perhaps
Not as
inaccurate because
complex
it's
as we are now.
what's say again?
Okay. Oh yeah, it wouldn't be as complex as today's biosphere because we wouldn't be here.
Yeah. Plausibly not. Yeah, I agree. Yes, this is definitely focused on plants. I don't know whether there's actual fundamental physical like reasons that something like mammals couldn't exist at higher temperatures, uh, or if it's a function of our particular biochemistry slash our particular, you know, trajectory we followed. Yeah, so yeah, but it's true. Mammals, as they are now, wouldn't exist in this world probably.
Thank you, Archie.
Oh,
Okay, great. Any other questions? Okay, Chris, you have your hand up. Go ahead.
Igor was first.
Oh, Igor was first. I'm sorry, I didn't see that. Go ahead, Igor.
Yeah, hi. Yeah, nice talk. Very interesting. I have a question. I assume that since you were working with Earth, you assumed 1 bar of atmospheric pressure. Do you know
mhm.
like what would happen like if you would go to slightly different atmospheric pressure? I guess I'm more thinking about exoplanets, but one could probably assume that the Earth could lose some of its atmosphere. So I assume that maybe like this overheating limit will change because of that or not? Is it like chemically based or it's like biologically based? So because your boiling temperature will change, so will it have an effect? Do you know?
That's an interesting question. Yeah, I don't think it's related to like approaching the boiling point or anything like that. So I don't think that there would be a boiling temperature thing. But I know that there's a paper from like 2009, Yuck Young's on it, where they look at the future lifespan of the biosphere and they argue that you can extend it by doing exactly what you just said, by removing pressure. Like they say, they basically like take they do the CK92 calculation out to the point where they reach 10 parts per million of CO2, and then they start decreasing the atmospheric pressure in order to like I think what happens is there's less Rayleigh scattering or no let's see. Or maybe it's there's less pressure broadening and that leads to cooling. And so that allows them to extend their lifespans
Mhm.
somewhat. But I don't know of like a mechan the one thing I can think of that might like systematically affect your pressure that would be like related to the calculations I'm doing would be that, oxygen is 20% of your pressure. And if you're changing your oxygen level, then you could have significant change in your pressure. But yeah, I don't know. I don't know if there'd be any direct effect on like the biochemical functioning just from the pressure itself. It's an interesting question. I'm not sure.
Okay.
But it would affect the climate. It would definitely affect how just the climate set
Yeah,
points.
climate of course will be affected. I was just thinking like, is there a biological effect?
Yeah,
Okay,
that
why don't we let Joao go since you already asked a question, Chris, and we'll come back to you if we have time. Go ahead, Joao.
Yeah, because I want to pull a little bit to my field. I'm more from plate tectonics. So my question is, when you consider these time scales, so you would expect to see some changes also in terms of geodynamics, so
Mhm.
of mental, that will impact the amount of volcanism. And my question is, did you consider that, or could you consider that, especially if you go for 1 or 2 billion years? And kind of open question or a challenging is, will be any feedback back on plate tectonics? Would you imagine something like that?
Oh, that's interesting. Yeah, I mean, so the first question, I we don't have like any kind of dynamic model where we have like the outgassing rate changing according to, some cooling in the interior or something like that. But I do, I did a set of calculations where I just run it with different outgassing rates, which would,
Okay,
that at
account
least
for that.
it gets, yeah, some part of what your response would be to lower outgassing rates. But the idea that there might be a feedback is interesting. Yeah, there's been the suggestion that like uh that the initial oxidation was like related to plate tectonics, right? Like people have argued that who's there's some Dutch guy who has a few papers arguing that like plate tectonics may have been triggered by the onset of oxygenic photosynthesis or something like that. I don't know. I haven't thought at all about how it might
That
feed
sounds
into
like
the functioning of it. But
rubbish.
yeah, yeah. I mean, maybe I don't know. What's his freaking name? Oh, he's written some
I
about like the faint young sun.
I think Mike Kern is even recently he came. This is Americans from Caltech. He
Oh,
revived this idea, but yeah.
oh, interesting. Um, Crap.
It's
Well, I'm
okay.
gonna
No
ask
worries.
some more
There's a,
questions. Yes, I'm gonna look for this paper though.
Okay,
But
why don't you go ahead, Chris, and ask your question?
Oh yeah, just two quick questions. But one, yeah, I was thinking with the Igor, with if you were thinking about the decline in oxygen, I think you're right that the pressure broadening wins over the Rayleigh scattering, so it would cool a little bit. But if you had a well, two things about the moist greenhouse, you probably know, or I'm sure Jim well, but if you had a like a 700 something millibar atmosphere that was just modern nitrogen, and the oxygen went away. If your planet was just a few cacti, I don't know if it could support support a big oxygenated atmosphere. Uh, if the moist greenhouse threshold would probably change a little bit because you could just
yes,
hydrate the hydration threshold would change at lower pressure. But also once you're in a moist greenhouse, I don't know if that's the cutoff for habitability because you still have a long time before the water leaks out. So
it's true.
yeah, uh, yeah, it was kind of a question, kind of a comment. I'm just like thinking out loud about those effects. But the other question was if that TE, presumably it's a function of time as well as continents move around and stuff. So if you have some period of like 100 million years where the continents are clustered in some configuration or in such a way as to enhance weathering, if if it's just easy to just terminate plants over some 50 million year interval, as we approach the next billion years, if it's kind of like an end game, if you only do it once in that future history, since your results are so, it seems like the weathering is so sensitive to the parameters, but the moist greenhouse stuff isn't. And so, uh,
Yeah, no, I agree. One of the one of the like extensions of this that I hope to do is to take um low scar and essentially do the same calculations but allow for perturbations like lips basically because which is you suggested a weathering perturbation. I was envisioning outgassing perturbations, same concept, just yeah, to see like if you just throw in stochastic increases or decreases in weathering at approximately the right you know well, Michael Way's paper about the lip, co-occurrence stuff, where they've got statistics for how often lips happen, and they've suggested that they may be, responsible for driving a lot of planets uninhabitable. And I'm curious as to how they might affect these results as well. Just adding in randomly distributed events like that, so it could shorten things a lot. Uh,
Okay,
yeah.
great. All right, David, go ahead.
Yeah, great talk, Graham. My question is about sort of time reversibility of this. So I think I asked you this by correspondence, but I'm not sure I quite understood your response. But yeah, if you play the tape backwards, certainly if you look at like these plots, it kind of implies everything's falling away in the future. And so that makes me think, well, if I went back in time, the bioproductivity peak would have been in the past. Or do we happen to live at the apex of bioproductivity. So just sort of if you time reverse these calculations, how consistent are they with what we know before? Are we really at a peak? Or, can you give me some insights into going backwards?
Yeah. So the model as it is right now, I certainly couldn't just run it backwards because so running into the future, you're basically going into an increasingly stressful environment where you're not in a nutrient limited situation. But if you run it into the past where you got lots of CO2 and it's really nice, the climate's nice, then I think what's going to matter more for the ultimate productivity is like nitrogen and P release in the soil. Hydrology will probably matter more. Basically, just things that I think kind of cap the productivity, when you don't have these environmental constraints, CO2 and temperature, you're going to have other constraints that I completely don't account for in this model. So if I wanted to run it back in time, I would need to add a few components, I think. Uh, I
Okay.
doubt we're at a peak in productivity because if it weren't for this last century, we would be at like among the lowest CO2 points in the history of the Earth. That it might have gotten down to maybe 200 at some point during the big time glacier stuff in the last million years. But we're really in the range of like lowest CO2 ever. Um, uh, so I would really be surprised if we're at some kind of peak in productivity. I think it was likely higher in the past. But yeah, I think there are both water supply and nutrient supply would provide different caps that you would need to account for if you actually wanted to figure out kind of if you wanted to find, okay, it peaked at X years in the past or something,
Mhm.
which is a super interesting question. But current model couldn't do it, definitely.
Okay.
But a few with some tinkering it could. Like I think like the that Ozaki and Reinhard paper that I mentioned earlier, because I've been asked about the oxygen point. This Ozaki and Reinhard paper has a pretty broad biogeochemical model, and that has been used to reconstruct the Phanerozoic. So, like for example, that model could be used to approach the question you asked, because it's got more components. But yeah,
Okay. Thank you.
was there another point to that question? Did I only answer
No,
half?
that was it. Thank you.
Okay, RJ, I think we're about
I
out of time. If you have a
I just
very quick
wanted
question, Nancy.
not I just wanted to follow up on the comment. Not only, the water and nutrients, but also the cover of the plants over the surface of the planet changes. So that's also consideration.
What do you mean? Oh, you mean like desert versus uh, whatever, nice
Like
landscapes with biomes?
liking the greening of the higher latitudes with warming,
Yeah,
back carbon for example. Yeah.
totally. Yeah, I agree with that. I want to do eventually a GCM with like a landscape model and actually see kind of how that spatial component plays out. Because I think, you could have swan song biospheres at your poles, for example, like that might allow things to last a lot longer than the global mean suggestion. Although at the same time, when you're getting really hot, your temperature is homogenizing over the planet, and so uh, maybe less of an effect than it would seem based on modern Earth. But yeah, I agree. Uh, um, yeah, and the greening of the poles would, yeah, that's you might have kind of a future in. Yeah, that's another point about when was the maximum productivity of Earth. You can aren't there like can't we see that there were crocodiles in Antarctica and stuff during the Eocene? I'm sure that the productivity was higher then. For example, just more land, more stuff growing.
Okay, great. Well, thank you so much again, Roger. This is really a wonderful talk, and I appreciate you making the effort. I know it's a bit late for some people, so
It was
Yeah,
super fun.
that was awesome. Thank you. Thank you. Great.
okay,
Thanks for inviting me.
absolutely.
And yeah, anybody has any more questions or wants to talk about stuff, feel free to contact me. I think I failed to put my email on this, but it is AREJAY Graham at uchicago.edu.
Awesome.